Algorithm breakdown. 1. Longest increasing subsequence, list, from left to right. We calculate the length of the longest increasing subsequence starting from each index, moving from left to right. This gives us information about the increasing slope on the left side of the potential mountain peak. 2. LIS from right to left. We reverse the array and calculate the list again, this time from right to left. This gives us information about the decreasing slope on the right side of the potential peak. 3. Identifying potential peaks. We iterate through the array, looking for indices where both the left and right list lengths are greater than 1. These indices are potential peak points. 4. Calculating removals for each peak. For each potential peak, we calculate the number of elements to remove, total underscore elements, left underscore list underscore length, right underscore list underscore length plus 1. 5. Finding the minimum removals. We iterate through all potential peaks and choose the minimum number of removals. Code walkthrough. Insert code with clear explanations, highlighting key points. Time space complexity. Time complexity, O, n squared, due to the nested loops in the list calculation. Space complexity, oxygen mononitride for storing the list lengths. Conclusion. By effectively utilizing the concept of longest increasing subsequences from both ends of the array, we can efficiently determine the minimum number of removals to form a mountain array. This problem demonstrates a classic dynamic programming approach and highlights the importance of recognizing